This last podcast on acids and bases deals specifically with salts. Now, salts are basically ionic compounds, and by definition they form during a neutralization reaction. However, not all salts have a neutral pH. So we're going to take a look here at all the different types of salts, look at the makeup of the salts, and then see if we can determine the overall pH, and then give some help here in this podcast as to calculating the pH of these salts. So let's start with those salts which form from the cation from a strong base and the anion from a strong acid. So that would be KCl, so the K from KOH and the Cl from HCl, and that's a strong base and a strong acid, and your resulting salt would be KCl. KNO3, NaCl, and NaNO3. Now when these salts go into solution, they dissociate into the cation and the anion. Neither of the two ions, though, reacts with water to create anything that would change the pH. So both of these ions are considered neutral, and the pH of the solution should be neutral. So these ions would simply dissociate in water, and neither of the two ions would interact with water in any way to change the pH. So again, this is the cation from a strong base, anion from a strong acid. The next group of salts, these salts result from the formation of a cation from a strong base and the anion from a weak acid. So if you look at sodium acetate there, the sodium would have come from sodium hydroxide, which is a strong base, and then the acetate ion would have come from acetic acid, which is a weak acid. When these salts dissociate in water, the cation does not interact with water. However, the anion will interact with water. So the acetate actually picks up a hydrogen from the water and produces OH minus in solution. This OH minus in solution then makes the solution basic. And you can calculate the pH of the solution by simply knowing the initial concentration of the anion and then setting up an ice table. Now, because this reaction produces OH minus, you would need to use the KB, products over reactants, get the OH minus concentration, and then calculate the pH from there. So again, these salts, you simply use an ice table, and you base your calculations on the initial concentration of the ions. Now, the next group of salts would be those that form from the cation that is a conjugate acid of a weak base, and the anion from a strong acid. So in other words, NH4Cl. The NH4 would form from NH3, which is a weak base. It picks up a hydrogen. And then the Cl would come from HCl, which is a strong acid. And so these salts typically will be acidic in solution. The NH4 plus will interact with water. The Cl minus, however, will not. And then the same is true of ammonium nitrate there. Ammonium will interact with water. The nitrate, however, will not. So the acidic cation acts as a proton donor, the ammonium, and it gives up an H plus in solution, and then you get NH3 formed. The H plus then will make the solution more acidic. Once again, you can use an ice table, and you have your initial NH4 plus concentration. Set up your ice table. Because this particular reaction is producing H plus, you would want to use the Ka to solve for the X, which that X then would be your H plus concentration. Now the next group of salts are a little more challenging. This particular type of salt that you see on the screen, both parts of the salt interact with water. So the cation is the conjugate acid of a weak base, the anion is the conjugate base of a weak acid. So you're going to get interaction from both the cation and the anion. And then the pH is sort of dependent upon which is stronger. And we're going to look at 3 examples. Now, as far as calculating, we won't do a whole lot of calculations with these type of salts. We will work more with those first 3 groups that we looked at. So if the Ka for the acidic part of the salt is greater than the Kb, then the solution is acidic. So in the case of NH4 plus and C2H3O2 in minus in ammonium acetate, you would be looking at the Ka for NH4 plus. Second situation, if the Kb for the basic ion is greater, so this would be in the example above, if the Kb for the C2H3O2 minus is greater than the Ka for NH4 plus, then the solution will be basic. So, and it sort of makes sense. Ka is greater, you get an acidic salt. Kb is greater, you get a basic salt. And of course, logic follows. If they are equal or very close to being equal to each other, then you end up with a neutral solution. Again, we won't do a whole lot of calculating with this particular salt, but there's the basic breakdown for acidic, basic, and neutral. Now, the very last group here, this is a sort of an unusual kind of salt formation, and it involves a complex ion. It involves a cation that's a highly charged metal, so that's typically in your transition metals. It's iron which is in the middle of the transition metals, iron and then to the right, so basically that area. These particular metal ions will become hydrated when they interact with water. So here's an example. This is aluminum chloride, and it goes into solution, interacts with water. The aluminum actually will complex with the water, and you'll get that complex ion that you see on the screen with the +3 charge, and then chloride ion produced. Now, this highly charged cation in this complex then will also then produce a conjugate base and give up a proton. So these types of metals will complex with water and with hydroxide, and then you'll end up with an H plus being produced, and so therefore the solution ends up being acidic. Okay, so for salt you kind of have to look at the makeup of the salt in order to determine whether that salt will be acidic, basic, or neutral, and then how you would go about calculating the pH. Now, one last little comment on acid-base properties, and that is, as you increase the number of oxygens on the polyatomic ion portion of the acid, you actually increase the acidity of that acid. And so we took here on the screen the acids containing chlorine and oxygen, and note the arrow at the top, they're increasing acidity. So as you add more oxygens, the solution, the acid solution, becomes increasingly more acidic. And this is true for other acids other than just those containing Cl. So you could look at H2SO3 versus H2SO4. When you add another oxygen there, you've made that particular acid more acidic. Same with H3PO3 and H3PO4. You add an oxygen there and you increase the acidity of the acid.